Okay, so this actually isn't where we left off. We did this slide. This is the last slide we did. I just want to kind of get the ball rolling, kind of remember what we talked about. Gosh, was that yesterday? It was like a lifetime ago. Okay, so this is an electrochemical cell. We have an anode and a cathode. The anode is where oxidation occurs, and the cathode is where reduction occurs. We talked about oxidation numbers. So of course, here's copper going from a 0 to a +2. Here's silver going from a +1 to a 0, right? So silver is being reduced and copper is being oxidized. So the copper being oxidized must happen at the anode. It's all about vowels and consonants. We kind of talked about that. And we said that actually, when you look at a table, and we're going to look at some more tables, all of the tables are for reduction half reactions. Okay, so if you look it up for copper, okay, what you're going to see actually is a positive 0.340 is the reduction voltage for copper going from a +2 to a 0. So if we need it for oxidation, we swing it around the reaction arrow, and we go ahead and change the sign of the half cell potential. And then we said that if you want to know for the whole cell, you take the oxidation plus the reduction, the anode and the cathode chambers, you add them together, and you get the overall voltage for the cell. So I think this is so cute. See this right here, this little voltmeter? Okay, that is actually matches up, so that's kind of fun. Okay. Now these are under standard conditions. Here today, one of the things we're going to tackle is non-standard conditions. The biggest thing for non-standard we're going to talk about is if the molarities are not 1 molar. Okay, this is where the molarities are 1 molar. Look. Okay. Non-standard conditions are going to kind of attack that a little bit. Okay. So we're going to do another example, okay, before we get to non-standard conditions. And we're going to go with zinc and copper. Okay. Now as they're written here, they look like they're both being reduced, right? Okay. But if it's going to be a cell, you got to have one's being oxidized and one's being reduced. So right off the bat, we're going to have to identify which one's going to be state reduction, as in the table, and which one we're going to swing around the reaction arrow and make it oxidation. We're going to pick strategically because we want the E of our cell to be positive. So we are going to actually leave the one with the highest half cell potential for reduction. We're going to leave that reduction, and the one with the lowest reduction half potential, we're going to go ahead and make that oxidation. I'll show you in this example. Then we're going to write the number 3, the overall balanced equation. Number 4, we're going to go ahead and add the two together and come up with the cell potential. And number 5, we're going to write that shorthand with the lines notation. So this is where we get to be strategic. If you look up table D or whatever, it's going to tell you that these are the reduction half cell potentials. Okay, so based upon what I said, we're going to leave the one that's the highest. Now the positive and negative counts here. It's not the absolute value of, it's the highest. So we're actually going to leave copper as reduction, and we're going to swing zinc, and we're going to make it oxidation. Okay, just based upon that. So here's zinc oxidation. Okay, zinc going from a 0 to a +2. And notice that the half cell potential over here is got a subscript OX, oxidation. And now instead of negative 0.763, it's positive 0.763 volts. The other half cell, we're going to leave reduction. Okay. So we line up the half cell potential for the reduction half. That's that plus 0.340 volts. And we add those two together, round it to 3 decimals to give us the overall cell potential. So the overall cell potential is 1.103 volts. Now remember, and this kind of blows my mind sometimes, but as long as they're at standard conditions, no, I was going to say something. Take it back. So anyway, The overall reaction is kind of a little bit kind of akin to what we talked about yesterday in lab. Okay, we add the two individual, the oxidation and the reduction reactions together. So that's actually, we're almost done now. We're down to that last bullet. All we got to do is write that shorthand notation thingy. And it goes from left to right, anode, cathode, oxidation, reduction. Okay, so here we go. So it goes from left to right, oxidation, reduction. So what's being oxidized? The zinc. What's being reduced? The copper. I think of the kind of the two double bar separating the two compartments.
Sorry, the anode's being oxidized?
Yes.
Is that what you said?
And yeah, and it's got the vowel thing going. Anode, oxidation, cathode, reduction. Consonant is the cathode reduction. And that's it. So here in a minute we're going to talk about electrochemical cells and the moles of electrons that are given up during oxidation and taken in during reduction. And can you see that number here is 2? We have 2 moles of electrons that are given up and 2 moles of electrons that are taken in. Okay. So this is showing you, see the 1.103 at the top? Yay, it matches the potential difference between the two cells. Okay. So there are many tables, and I just do 2 of them. So I show you this one, and then we skip the next 4. Remember, these aren't alphabetical, and so it makes it kind of hard if you have to find one, quite frankly. But they're written as the highest reduction half potential, and then the lowest reduction half potential. What's that?
So whose idea was that?
I know, it does make it hard. Okay, so what I did is a little bit different. I do want you to go ahead and do these because I think it will help you solidify the material for the exam. But for each of these 3 problems, there's A through D, and I only want you to do A and B for each of them. And we'll take a look at them right quick. And not to minimize their difficulty, but from what I could tell, they're all just a subtraction problem. So, if that helps.
I want us to do 20, we only have 19 and 21.
Yeah, so add 20. Yeah, thanks for... I couldn't tell in my notes, but I know last time I taught this, I went with including 20. So 19, 20, 21. And I'll show you what they look like. And we're clear to chapter 20. Okay.
So when are you going to write your own book?
What's that?
So when are you going to write your own book?
Right. So there's 19A right there. And I went ahead and it's written the shorthand notation. So, of course, we have oxidation reduction. And basically, you're going to use the tables, table 21, table 20.1, to go ahead and find out what the reduction half cell potential is for aluminum. And that's the one that you're going to swing around and multiply the E0 reduction by -1. Okay, and then down here at the bottom, I said, here's what you're going to use. I grabbed it from your textbook. Basically, you're going to add the 2 half cell potentials. So it shouldn't be too bad. It says, write the cell reactions, and then calculate the E cell. And 20 is similar. Same as number 19. Okay, and for 21, I went ahead and just kind of over top of the reaction showed you what we got. Of course, we would identify as the hydrogens as zero oxidation state. The fluorine and F2 are zero oxidation state. On the product side, we have hydrogen going to a +1, fluoride going to a -1. Okay, so we definitely have a redox reaction going on. In this one, you're supposed to calculate the E0 of the cell. Okay, so, oh, and it says which reactions will occur spontaneously. Do you guys remember? If the E0 of the cell is positive, then it's spontaneous. So I guess that's a follow-up question to A. Did I say A and B?
Yeah.
Yeah,
Okay, just do A.
just that.
Just A, yep. I meant A.
What did you just say?
Oh, yeah, if it's positive.
If it's positive, it's
Spontaneous.
Yeah,
spontaneous.
yeah, because delta G is equal to negative NF. Delta or E. So if E is positive, delta G is negative. Okay? All right. Well, let's finish out this lecture slides. So this looks familiar. This is what we've been using. For your cell, you're going to have an anode and a cathode working together, oxidation reduction. You come up with those two half-cell potentials, add them together to get the E0 for the cell. Now notice this is calculating standard cell potentials at standard conditions. And I already mentioned that I'm going to emphasize the concentration of the reactants and products in solution here in a minute. Okay. And we already looked at this. This isn't new. This is the change in Gibbs free energy of the reaction. The redox reaction is equal to negative N, where N is the moles of electrons times Faraday's constant times E0, and that should be like E0 of the cell.
I don't remember, is that constant on our sheet?
Yeah, the F, I think it is. No, well, you won't need it then.
Okay. Well, the other, that equation is though.
Yeah, the equation is.
Okay.
Yeah, I will make sure of that.
I mean, I can just write it down.
Yeah, don't think you'll need it, because I have the values of R on the sheet, so. Yeah, I think you're okay, which means you aren't going to use that equation.
Okay. Sweet.
Okay, so switching to non-standard conditions, it's a famous equation called the Nernst equation. And I have some versions of the Nernst equation coming up on the next few slides. And I was a little bit at a loss as to how, and I'll show you which ones they are. We go from the natural log of ln to the log base 10, and the looks like the constant changes. So anyway, I went on the internet and found a source that if you're interested in, we'll show you how that works. But the Nernst equation deals with non-standard conditions. Non-standard in concentration, and actually it could deal in non-standard in temperature too. But here in a minute, we're going to go ahead and sync that temperature at 25 degrees Celsius, just what we do. So what you do is you take the E cells, this is what we've been calculating, and from that you subtract this quantity. And this quantity, you recognize R as a constant, F is a constant, N is the number of moles of electrons that are transferred, or that are given off or gained during oxidation reduction. T is the temperature, and this Q is, this is like our QC. This is our equilibrium, it's describing our equilibrium. It's our snapshot. It's our reaction quotient. That's our reaction quotient we talked about before. It's our snapshot. So if you're kind of comparing the previous slide to this slide, this one's different. The T term has gone away. The R and the F term have gone away. They all went away. T went away because we're setting at 25 degrees Celsius. R and T went away because we just kind of balled them all into the same constant. Okay? So here we go. Now this is where I looked it up. I'm not sure why we do this, but they did it in Chem Wikipedia too. But instead of the natural log, if we go log base 10, and this is actually the equation we're going to use. This is the equation that you see on your sheet. that non-standard conditions specifically with regard to changing molar concentrations from 1 molar, the cell potential is equal to the standard cell potential that we've been calculating minus 0.0592 divided by the number of moles of electrons that are involved in your redox reaction times the log base 10 of the reaction quotient, Q. All right, and so that's what we're going to use. So like I said, I looked it up and I found a reasonably good source that kind of talks you through that. Okay. So just to kind of remind you how this whole thing works, if your cell potential, whether it's your standard cell potential or your cell potential at non-standard conditions, if it's positive, then your reaction is spontaneous, as written from left to right. If the cell potential is 0, then the reaction is at equilibrium. The rate in the forward direction is equal to the rate in the reverse direction. If it's negative, then it's non-spontaneous as written. But if you want to make it spontaneous, all you got to do is rewrite it from, swinging around the reaction arrow. So we're going to look at the specific case where it's at equilibrium. And I don't have the proof to kind of show you all the steps, but if it's at equilibrium, then the Nernst equation kind of does something interesting. Well, actually, if it's at equilibrium, then your snapshot, your reaction quotient, QC, is really KC, okay? And then if we go ahead and kind of move E0 of the cell to the other side, and then go ahead and multiply by n over 0.592 both sides, you end up with this. I guess it's not so complicated. We get the log of your equilibrium constant K is equal to n times your standard cell potential divided by 0.0592. Okay. So that's kind of fun, and actually we've got an example where you're going to be calculating one of those coming up. Is it the next slide? Yeah, so let's go ahead and do one. So in this case, actually this is one, I looked at my notes, I'm like, that sounds familiar. If you go clear back at the beginning of part 5, or you'll see actually looked at silver and copper in 2 different cells. And can't remember which was oxidation, which was reduction. But I'm going to refer to that standard cell potential that we calculated before. So we're going to look at this particular cell in 2 scenarios. We're going to look at a scenario where the molar concentration, instead of 1 molar, it's 0.1 molar each in the silver ion and the copper 2 ion. And then we are going to go ahead and make them lopsided. We're going to leave the copper 2 ion, 0.1 molar, and we're going to jack down the silver ion to 0.0010 moles per liter. And we're going to come up with those, for those non-standard conditions, we're going to come up with the E of the cell, okay, using the Nernst equation. And then last but not least, when we come up with the cell potential, then we're going to go ahead and use the K, that last equation, to knock out K, okay, which we could have done without the non-standard potentials. Yeah, so this is what we looked at clear at the beginning of this unit or part yesterday. So the copper is going to be oxidized and the silver is going to be reduced. So the copper is going to be at the anode and the silver is going to be at the cathode. Our overall standard cell potential is 0.460 volts. I should be saying volts. Okay. So the Nernst equation, to remind you what this looks like, there's your Nernst equation. So just so we're all on the same track, that value that we have at the bottom of the previous page, that's going to go right there. That's your standard cell potential. N is going to be actually 2 electrons. Okay. What we need to spend some time remembering is what are we going to do with that reaction quotient Q. That reaction quotient Q is going to look at, I know it's not an equilibrium, but remember how we said it's always, you take the molar concentration of the products raised to their stoichiometric coefficients, and it's divided by the molar concentration of the reactants raised to their stoichiometric coefficients. Okay? If it's a solid, it doesn't appear. Remember that? How that works? Okay. So that's the sort of backdrop we have for figuring out that Q term.
Sorry, why is the N 2 electrons?
If you go back to the previous slide, did you see the 2 electrons there?
I do, but I don't understand why.
And this kind of goes with kind of what we did yesterday. We said that the number of electrons that are giving up have to be equal to the number of electrons that are taken in. So by golly, if with 1 mole of copper, to form 1 mole of copper plus 2, if you need 2, or if you create 2, those 2 need to be consumed. So then that's why we bump up our silver to 2 silvers, taking 2 electrons to form, or 2 silver ions, taking 2 electrons to form 2 silver solids. So that's why it's 2. Yeah. So what are we going to do with the Q? Well, we're just going to go ahead and write our QSP expression. Again, it's products over reactants. If there's a solid or a liquid, it doesn't appear in your KC expression, so it doesn't appear in your QC expression either. A very common mistake, and I could probably say I do this too, but do you guys see where the balanced equation has, the balanced equation has a 2 in front of the AG? It's a subtle thing. So now all we got to do is plug in, like that 0.1 molar goes down the bottom, that 0.1 molar goes in the top. Okay? If you didn't square the silver ion, you'd get 1 there, wouldn't you? But it's squared, so that's why you get 10. So the value of 10, which is the ratio, well, the value of 10, which is your QC, goes in there for your QC. So now we're ready to knock this out. So the non-standard, the cell potential at non-standard conditions is equal to the cell potential at standard conditions, 0.460 volts minus 0.0592 divided by 2 times the log of Q, which is 10. I'm not sure how I rounded it. To me, it looks like I need 2 significant figures. I bet I gave myself 3. Yeah, I'm kind of liking 2 sig figs for that. But I can live with that. So we got 0.430 volts. Okay? So does it seem like it's spontaneous? I agree. Okay, let's do the other one. The other one will be very similar. The only difference for the next one is going to be this right here, isn't it? That's the only difference. So here we go. Again, the standard cell potential is still 0.460 volts. We still have 2 moles of electrons created and gained. Okay, so now when we plug in the molar concentration of our copper, it's still 0.10, but the molar concentration of our silver ion is 0.0010, quantity squared. When we divide that out, round into 2 significant figures, we get 1.0 times 10 to the 5th is our Q value, or QC. So now we're going to plug that back into the Nernst equation and knock out the potential of the cell at these non-standard conditions. So it's the same as it was before. So at these non-standard conditions, it's the standard condition cell potential, 0.460 volts, minus 0.0592 divided by 2, the moles of electrons, times log of Q, which in this case was 1.0 times 10 to the 5th. Should be rounded 2 sig figs, but rounded to, well, maybe, no, rounded to 3 significant figures. Actually, maybe it is, I don't know. I get 0.312 volts. Did it go up or down? It went down. Yeah. Is it still spontaneous? I'm liking it. Okay. So the last thing we were tasked to do, I guess, was to come up with the equilibrium constant, the K. So this is why when I was mumbling to myself, I'm like, you know what? We don't need to have those other cell potentials to get to K. We just needed the standard cell potential. So plugging in N and E0, we get log of K is equal to 2 times 0.460 divided by 0.0592. Log of K is equal to 15.5. And then this is where we get to do our law of logs magic. We take 10 raised to this quantity, that's equal to K, is equal to 10 raised to 15.5. So K is equal to 10 raised to 15.5. So your K is 3.47 times 10 to the 15th. One of the things I struggle with is, you know, that clearly that redox reaction has not been written with a two-way arrow. It's always been a one-way arrow, one-way arrow. And Ks are talking about, yeah. But at this point, this is where you're supposed to go, aha, that's why it's a one-way arrow. I mean, that lies relatively far to the right. So, just one of the things I'm like, now why did I do that? So anyway. Okay, so, no, this is not worth, I'm not doing extra credit points over. I meant to erase this. This is for regular credit. Do you want it for extra credit? No, this is for regular credit because I only had, I'm taking it down to just 3. I know, it's so hard.
Made me think of a comedian.
Oh, you and your comedians. Okay, so we'll take a look at what those look like. 2026 looks like this. 2026A. So, just for A, you need to, just for kicks, you need to write the equilibrium constant expression. So I thought this was good practice for you. That's why it's not extra credit. So write the KC, and I kind of, for shorthand, wrote the molar concentration of the products raised their stoichiometric coefficient divided by the molar concentration of the reactants. That's not an N, that's like a little caret raised to their stoichiometric coefficients, just like we've been doing our K, our Qs. And you need to determine the value of K for that redox reaction using, so you're also going to have to come up with the standard E0, aren't you? Standard cell potential. Let's see if I have that in my hints. Yep. Oh, no, I guess I don't. Yeah. So, by the way, your textbook uses Z instead of N, so don't let that throw you off. And this is the natural log, not base 10, so that's why the constant's different. So that'll be good practice. 37 looks like this. use the Nernst equation, given this molar concentration, the 0.18 and the 0.85, the molar concentration of the aluminum ion and the iron ion. So you're going to first have to somewhere in there come up with the standard cell potential. And my hint to you guys, and I double checked this, make sure I wasn't giving you bad advice, but the number of moles of electrons is 6. You remember the step that we did in balancing redox reaction equations using the half method, where we had to reconcile the lowest common multiple? Is that it? Okay, good. The lowest common multiple. So just doing it shorthand, this is really ugly, okay? But can you see where there's 3 electrons here? Okay, aluminum, it's a 0, and it's a +3. And then over here, it looks like 2 electrons, okay? And the lowest common multiple is going to be 6. And then the last one, for regular credit, looks like this. Oh, very similar to 37. And I told you the number of moles of electrons, 2. So does that make sense? The number of moles of electron is 2. So just kind of looking at here, the manganese, okay, I got 2 electrons here. And the chromium, let's see, I only got 1 electron there. Does that look right? 1 electron, okay? But that's going to be a case where I'm going to scale up my chromium to make it 2 electrons. So the lowest common multiple actually is 2. Okay. And that's all I got. Is that it? That's the last slide. Dun, dun, dun.